Hi. For this lecture, this is the title, Propositional Equivalences. Sounds a little bit heavy duty, but you'll see there's quite a lot of formulas involved in this thing, and luckily it's open book, so it's not something that you do have to memorize all these formulas, but you need to know kind of what formulas are available. It's sometimes just relying on the fact that you have formula sheets is not always the best solution, because you need to know right on the spot whether this is something you can be able to use or not. Okay, there are a lot of things in this section, and again, some of the things I will skip. You will see. Okay, so let's start with what does this mean? Well, before I say this, let's talk about two things that we have already encountered. Namely, we have seen that there's sometimes propositional expressions that are always true. And here is an example of something like that. So if you look at the P or not P. Why is this always true? Well, let's make the truth table of it, right? It's very easy to make the truth table. There's only one variable. So this is P, this is then not P. P or not P. Well, that is only false if both are false, but that's not the case. So, because here one of them is true and here one of them is true. So, this is what the situation we're in here, that we have all ones in this column. That means that no matter what reality you're in, remember we think of this as scenarios or possible worlds, this statement is always true. And so we give a name to the statement a statement that is always true is called a tautology. Tautology. I mean, the word in common day English means also something. It means something that is trivially true, that is always true, tautology. Okay? So tautology is a statement that is a proposition that always is true. And of course there is a converse of it, that's the so-called, what we call contradiction. Something that is always false, no matter what you put in there, you get always zeros. So an example again, so this is an example, right? This is an example. I'm not saying that this is an example. Another example here is P and not P, because if you look at the truth table for this guy, 0, 0, 1, for an and, you can only get a 1 if both are 1, but that's not the case here, neither there. So here we are now in a situation where we have zeros all the time, so this is what we call a contradiction. So this is always false. Of course, this is something important, right? Because we do want to make true statements. So we would like to make tautologies, so that no matter what the circumstances are, this is always going to be true. Now, you might kind of doubt that this exists, but you'll see there are so many of them. Okay? So that's the two concepts, but the main concept here was about propositional equivalences, so I need to explain what that means. Now, so let's suppose we have two statements, A and B are propositional statements. I'm using different letters than P and Q. P and Q are my variables, right? And A and B are one of these. So this is, for instance, what I would call A or something. So if these are statements, then we say that A is logically or propositionally equivalent, but logically is a word that is often very also used, and in fact some people just say equivalent to B means that whenever A is true, B is true, and whenever A is false, B is false. Okay, so in other words, as far as truth is concerned, they behave the same. Oh, you say, I remember that there is one of these things. This means this one, right? Because A, even only B, is true exactly when A and B have the same truth values. So what this means is that A is logically equivalent means exactly that this means that this is always true, but we have a fancy word for that now. It's a tautology. Okay, and the notation that we use, well, we can use this notation with the even only if error, so A, but often is also this notation. Again, perhaps this is not clear at all what this means and how this works, so for now it's a definition, but it becomes hopefully very, very quickly clear. And here's the first one, and this is actually already a very important examples. These are called De Morgan laws. Now, De Morgan is a mathematician and logician who came up with these formal laws, and you can read about him in the textbook. There's always, you remember, we're going to see a lot of mathematicians or scientists that are mentioned in the book and that are discussed in the book, and you have to choose one of them at some point and write a report on that. I'll say more about it when we get to this writing assignment. Okay, so De Morgan's laws. So what is this? This is the following, namely P and Q. What happens if we negate something like that? Well, the Morgan law says that it's logically equivalent to not P or not Q. Let's think about this first for all. P is I had coffee, and Q is I ate a bagel. I had a bagel. Okay? So, I had coffee and I had a bagel. That's P and Q. What's the negation of that? In which situations is this not true? What is the negation of I had coffee and I had a bagel? Well, it's not true if I, for instance, didn't have coffee, but it's also not true if I didn't have a bagel. And it's definitely not true if I had neither one. Okay? So, the negation of I had coffee and I had bagel is I didn't have coffee or I didn't have a bagel. It could be that I had coffee, but I didn't eat a bagel. So one could be true, but not the other. And that's why it's an or. So what this means is that if you have a not in front of an and, then it becomes the or. So the and flips into an or, and you get the negation of the variables. Now, that's one of them, but it comes with a companion, namely, these things are rather symmetric. What is this then, you think? Well, you try to figure it out, perhaps on an example first with the coffee and the bagel thing, but I'm going to write it up here. This is not P and not Q. So you see what happens, right? In a negation, if you negate an and, it becomes an or. If you negate an or, it becomes an and then you take the negations of the propositions. These are called De Morgan's laws. And I'm saying that here, so what I'm saying is that this expression is logically equivalent to this, and this expression is logically equivalent to this. How do we know this? Well, one way, and I haven't coming back here, how do we show that something is a tautology? Well, I gave examples, but it was very, very simple examples. But I told you what the key feature is. To find a tautology, we need ones in a whole column. And in what we did, well, we need to do this here, okay? That is for a tautology. Now, there's another way of saying the same thing. Logically equivalent, so, sorry, I said it, but I didn't write it down. A and B have the same, so that means that A and B have the same truth values. So this is actually, in other words, an easier step. Instead of showing that A even only B is a tautology, what I actually only need to do is make a truth table for A, make a truth table for B, and compare. They should be the same. So, in other words, this means, let me write it up. So I'll write it here. This means that the truth tables for A and B are the same. I mean the columns for A and B are the same. This is how we can practically figure out that something is a tautology. It's not the only way, but it's a way that works, at least for us, because we always deal with 2, 3, perhaps 4 variables, and it's all feasible. But think about it, if you have to deal with 10 propositional variables, that's 2 to the 10 rows in your truth table. That is about more than 1,000. That's not something practical anymore. Okay, and therefore there are other things one needs to do. We'll talk about that later. But now, for now, so our gateway to showing that something is logically equivalent is just simply this. make the truth table of this, make truth table of that, and compare, see that they're the same or not. Okay, let's do that. Let's get it at work. So I keep this one up here. I'm going to do the first one, right? Okay, let's perhaps get rid of this one here. I'm going to get rid of this thing here and then move this a little bit here. Oops. So that I have them both here. Those are my two De Morgan laws. Okay, I'm going to show you. Okay, I'm going to show you now, but these are such important laws that we're going to later use them all the time. Okay, it's not just something that I verify once, but this because if they have names, then they are important. If they don't have names, we will see some then that don't have names. They are not important, and therefore you don't need to write them. You just work them out as they come to you. But this one's okay. Let's do this. PQ. So there are only 4. That's not too much work. 1 1 0 0 1 0 1 0. Okay. What do we need to do? P and Q. That's the first component, right? That's 1 0 0 0, right? And N is only true if both are true. Now I'm going to negate this, right? I'm now working on this part here. So I'm going to negate this. So negate P and Q. Now negating means just flipping the digits. So that's 0, 1, 1, 1. Okay. So remember I'm doing the first one, right? So I'm working on this guy here. Okay, this is done. Now, to show that this is logically equivalent to that, I need to make the truth table for this guy and then show that it looks exactly like this. Okay, so not P and not Q. We need those guys first. So let's do them first. They're very quickly done. Not P, and here is not Q. That is just flipping the digits. And now I have to take an OR of those. So not P or not Q. What is an OR? Remember, an OR is true if one of them is true, or perhaps sometimes it's better to say when it is false, when both are false. So let's look at, in other words, what we're looking for is a 0 in here as well in there. If we have the same 0 in both columns, then this expression will be false. And this is happening in this row, and that's the only row, right? So we get a 0 here and a 1 there. Because that's the only one false, the rest must be true. That's how I always work it. I also have a review on truth tables quiz, so you'll see a bit more how I'm building truth tables. So if you're a bit kind of taken aback by these truth tables, go look at that review video of truth tables. That's a review video for the quiz first, because that helps you then understand this. Now comes the clue, right? Are these two expressions, let's do the pink, is this logically equivalent? Well, is this column the same as this column? Yes, it is. So that's how you prove logical equivalence. I'm not going to do the second. I'm going to probably do some homework problems and so on. There is another important one, although it doesn't have a name. I'm going to show you another one, namely P then Q is logically equivalent with not P or Q. Which is kind of a bit weird, right? Because one side we have an implication and the other side we have an OR. So you kind of wouldn't think that if then can actually be written in an OR statement, but it is. This is what it says, right? So instead of saying if I drink coffee then I have a bagel, I can say either I don't have a bagel. No, sorry. If I drink coffee then I have a bagel. That was the thing, right? Is it logically equivalent that I don't have coffee or I have a bagel? It doesn't really sound the same, and you have to think long and hard about it, but when you do this with truth tables, it's the undeniable truth, right? Okay, let's do this. So P and Q, 1 1 0 0 1 0 1 0. Okay, what do we need? P then Q. Oh, I know how to do that. It's 0 exactly when the first is true and the second is false. So exactly in this situation. So we get a 0 here and everywhere else it's 1. Okay. Now in the other one I need not P. So I need to do this first, which is just flipping the digits. Easy, easy, easy. And then not P or Q. So not P or Q. Okay. And that is true. Remember, an OR is true if sorry, let's say it's better to say when it's false. It's false when both are false. So we're looking for zeros in both. So we're looking for a zero in this guy as well as in this guy. Okay, so perhaps it sometimes helps to mark them if they're a little bit far apart. So we're talking about these two columns and we're looking for a common zero because that will then mean a zero also. So this is the common zero, and therefore everywhere else, that's the only case, is a 1. Doop, 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 doop. So are these two now logically equivalent? Well, what this means, this is logically equivalent to this if this is the same as that. There you are, it's the same. Cool, no? Okay, so that's, and as I said, this tells me, what I just proved is that P then Q can actually be the operation if then, the conditional operation is actually not necessary. With not and or, I can write it down already. And therefore, now you could say, okay, what about the and then? Well, actually the and can also be written down using this here. If I take, okay, sorry, I have to, I'm jumping a little bit ahead. Let me not do that yet. Okay, so. Okay, so I'll do one more perhaps. Let's see. Yeah, let me do this one more. It's good to do one more here. It involves 3, so it's a little bit more work. Again, it doesn't have a name, but this is, well, it has a name, but I'll talk about the names later. P or Q and R is logically equivalent with P or Q and Q or R. Oh, sorry, no, that's a mistake, sorry. I wrote it wrong, I was looking at something else, P or R. So this is called, and I'll point it out later again, is distributivity. Namely, what it means, let's look at it. It says that this or, you can distribute it over these two, so P or Q, P or R, and then in the middle you get this sign here. So a little bit like multiplication and addition, okay? But again, the weird thing is that this is or, what we say or distributes over n, but by symmetry, this other thing is also true. So there's a simple formula where the ors becomes n's and the n becomes ors. Now, okay, let me do this one. Let me show that this is true. So again, we have to make a truth table. This time it's a little bit longer truth table. So P, Q, and R, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0. Okay. Let's break it down, and I'll start using a little bit of colors like in the review video. Q and R, that's the first component that I have to find, and that is true if both are true and otherwise it's false. So I'm looking for a 1 in both of these columns, Q and R, and that is here and here. And everywhere else is 0, so 0, 0, 0, 0, 0, 0. Okay. Then I have the actual expression, this one here, so P or Q and R, that gets a little bit illegible, right? So let me take a darker green. Okay, so how does that work? Remember, an or is false if both are in both columns you have falsitude. So you hit here and this. Okay, let me, again, it helps if I highlight these things that I know where to look. So I'm looking in these two rows and I'm looking for common zeros because that will result in a zero, total zero. So we see this happens in this case. In this case, and in this case, right? I got a little bit crooked here. Let me try to fix my crooked line here. Ooh, I lost another one. Okay, sorry. Let me fix it a little bit because I got a little bit distracted by it. Okay. So these are the. Oh no. Yeah, right. So I'm looking in this case. Let's see. Yes, okay, correct, right? So this means that all the other guys are ones. 1, 1, 1, 1, 1. Good. That's the left hand side. Now, what about the right hand side? Okay, that's a couple of expressions that we work out again. So P or Q. Let's start with that. That's one component, right? P or Q, that is an or. This is false if both are false. Now, they are next to each other, so I'm not going to align them. Let's get rid of this. So we're looking in these two columns for a common 0. This all the way in the bottom this happens. So we get a 0 here and a 0 here, and everywhere else is a 1. 1, 1, 1, 1, 1, 1. P or R, okay, I can do that too. It's kind of similar principle, but now I'm looking into this and this column with some zeros, and if you, I hope you, I'm not going to highlight it, it's kind of obvious, right? Oh, sorry, these are zeros, right? Here and here, right? These are the two occasions we have a common 0 here, common 0, and everything else you see, this is always, at least one is true, and therefore, these are all ones. Good. That's, oh, okay, that should have been a different color, but okay, it's now the same color. Fine. And then finally, let's put this guy together. So I'm not going to copy it. I'm just going to write with an arrow here. This is what I'm going to write there. It's an and between these two next to each other, so it's easy. And an and is false. An and is true when both are true. So you see, I always think about what is the best way for me to figure out how to make a truth table. For the and, I'm looking for the truth. For the or, I'm looking for falsitudes, etc. Okay, I'm not saying you have to do that, but trust me, it goes much faster if you do that. But you have to be correct, of course, right? Okay, so let's do this. What we need to look for, let's repeat what I'm looking for. I'm looking for it's an and, so I'm looking for a 1 in here and a 1 in there, then I will have truth. Okay? So that is the case here, 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 and here, and no longer, so 0, 0, 0. Now the big moment of truth, is this the same as that? In other words, is this column the same as that column? And there we are. Okay? So there are many, many, many more logical equivalences, and I obviously cannot look at all of them, so I'm going to show you here. This is from the textbook. They have also a lot of names. Not all of them are that important, so I'm not going to say too much about of some of them. The ones that we just talked about, let's look at the ones that are important for us somehow. Another one that I have not mentioned yet, but it's kind of obvious, just looking at the way truth tables work, is this one here, which is called the commutative laws. P or Q, Q or P, they are logically equivalent. And the same for the and. Okay. Also, when we are dealing with, let's look at the next one here. This is called the associative laws. That if you take 3 ors in a row, it doesn't matter in which order you do that. P or Q or R is the same as P or Q or R. And in other words, there are no need for parentheses. Okay. Do not confuse that with the next one, because here is a mixture of ors and ands. And if you recognize, this is exactly one of them that we just proved, right? This is the so-called distributive laws that we proved with, I forgot now which one we did. We did the second one, I think, right? Yeah. And the first one you see is very symmetrical, and it's true too. Okay? Oops, no, that's not what I want to do. That's what I want to do. The Morgan's law we just already discussed. They are very important laws. Then there are a couple called idempotent. Now the other laws are perhaps slightly less important, so I don't want to say too much about them anymore. But they're all true. And by the way, yeah, I should perhaps point this out here. You see, sorry, I have no pointer, so I have to kind of write each time when I do this. I don't think I have a pointer on this one. What is this? That's an eraser. I don't know what this is. Oh, that's just tip. No, okay, forget it. So you see this T and F here. This stands for a statement that is always true. In other words, a tautology. And F stands for something that's always false. In other words, a contradiction. Okay, that's what this means in these tables. I have pointed out to you that they use T's and F's for T for true and F for false, which makes it very, to me, look ugly. Ones and zeros so much easier. So please use ones and zeros all the time. Okay, this is very annoying, this thing. I have to figure out a better way to deal with this, but okay. Oh, I have to, sorry, I want to get rid of all marks that I make here. Okay, now I can. Next page. There are a lot of more. So you see, it's like it's like a sea of possibilities here. So here the first one again, my pointer, the first one is the one that I already proved. But there are many more involving P and Q. One that is kind of probably no, sorry, that's not what I meant to say. Yeah, one that is I haven't done yet, and I'm going to give it. It's probably one of the homework problems. Is this one here? The biconditional. We say that P and Q are true, even only if. And of course, when we say even only if, we think that if P then Q, and if Q then P. And that's exactly what it says, that these two are exactly the same. So that's definitely one. I hope it's a homework problem. If it's not, please check it out for yourself with the truth tables. Okay? So I think I don't need to show more on this, and let me go back to my notepad. Okay, I'm gonna put it back on this. Okay, so right. So where are we now? Yeah. So sometimes, and this is something that we'll do later, but I'm going to give you just one quick example of this. Is we can use this logical equivalences to build new logical equivalences. So let me just give you an example. So this I claim is logically equivalent with this. And this is sometimes even easier to think about. A negation is, and this is not so surprising. Remember, this not P then Q means when is the negation false? Well, we just said that when the first one is true and the second one is false. Okay, so this is something that we have been using. Now, how can we derive this? Well, we have seen before this one, right? That P is logically equivalent with not P or Q. Right? Let me go back to where we did this here. Okay. So once you have a logical equivalence, this means now you can apply to both sides operations. You can use them. They are the same as far as truth is concerned, so you can replace one by the other. In particular, not P then Q is logically equivalent with not P or Q. Right? What I'm just saying is, okay, I apply not to this, then I can apply not to that. Now, what happens if I apply not to an or? That's the Morgan's law, right? Where are my Morgan's law? The not of an or is the end of the negations. So we negate. So let's work this out, because this is important. The Morgan's laws we're going to use them so often, and there are homework problems that test you on trying to do that. That it is, we need to practice this. So this is logical equivalent. What can we say? To apply this negation, we kind of distribute it to the two propositions. So the not P. Okay, not P. Sorry, that is something I forgot to point out. Let me go back to it. I have to point it out to you. I knew I was forgetting something. Let's do this, and then here, this is the one. This here. This is a very important one. This is the so-called double negation. It's something that we all know. A double negative technically cancels out, right? I'm not going to do this means I'm going to do this, right? And this is exactly what this is. Not P is logically equivalent to P. Sorry for that I should have pointed that out. I forgot to point it out. Okay. Oh, no, I need to, sorry. Keep this clean a little bit. Yeah, now I can go back. Okay, so what does it mean now? Okay, that's what I'm trying to say. I'm going to do the not apply to the not. So we get not P, not P. And we also get the negation of Q, that's not Q. But be careful, the Morgan laws switch the operations. We started with an or. If we apply the not, then this becomes an and. So, and here. And now we lose this double negation. Not P, so not P is logically equivalent to P. And again, I can replace one by the other. So I'm replacing the not P by P. There's an and here. P and not Q. And look, I found this guy. So this is, sometimes you can do this without truth tables, and sometimes it is advisable to do it without truth tables, because it could be very, very lengthy to do this. So here is one more example. Yeah. Okay, yeah, let's do this one. P and Q, then P or Q. If you think about it, it's this. Okay, what? Sorry, so it's not logical equivalence. This is a tautology. This is my claim now. Sorry, I'm going to talk about tautologies. How do you recognize tautologies? Well, remember, this is where the truth table gives ones everywhere. I'm claiming this is a tautology. Sorry, so I'm now talking about tautologies. How do we do this? Well, let's make the truth table. P, Q, 1, 1, 0, 0, 1, 0, 1, 0. So P and Q, okay, very quickly. Please do this now, right? You should be able to do all this. So do this, pause the video, do this, and then compare what you got with what I said. Okay, so this is 1, 0, 0, 0. P or Q, that is 0 here and 1 everywhere else. And now we are the biconditional again. Let me remind you how does it work. We have this guy. So we have this one is the first one and this is the second one. What we're looking for is a 1 in the first and a 0 in the second. Then we have false. So where is this? Not here, not the second one, not the third one, not, oh, it doesn't happen. There's no zeros. What does that mean? So remember, this is what I'm trying to make now. Well, that means everything has a 1. 1, 1, 1, 1, 1. Ah, but that's exactly what I wanted, right? Remember, 1's everywhere. This means it's a tautology. So that's how you prove that something is a tautology. You show that it is 1's everywhere. And again, there are a lot of homework problems like that. And then finally, we have the notion of satisfiability. So let me do it like here. So we say A is satisfiable if it could become true. In other words, another way of saying that, if it's not a contradiction, i.e., meaning, i.e., it est, that's Latin, but that's meaning, it's not a contradiction. So, and this kind of tells you how you can find out that something is satisfiable. Namely, it's satisfiable if it's not a contradiction, and it means that there is at least one 1 in my column. Because if it's all zeros, then it's a contradiction. Okay, so satisfiable means there's at least one 1. So let me give you an example here. They are kind of lengthy. Okay, this is the one. I'll do this one. P or Q or R, and not P or not Q or not R. Now, first of all, you might say, why are there not parentheses with more parentheses? Well, remember we had associativity, and it means it doesn't matter in which order we calculate this. However, we have to choose an order when we do this calculation, right? So I'm claiming that this is tautology, right? Okay. Oh, no, sorry. Sorry. I'm not claiming it's a tautology. I'm claiming it's satisfiable. Sorry. Is this satisfiable or not? I mean, I'm not claiming it. Let's figure it out. Is this satisfiable? Is it possible that this can happen? Okay, so how do we do this? Here is P, here is Q, and here is R. One, 1, 1, 1, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0. P or Q or R? Well, as I said, I have to do it in 2 steps. P or Q or R. P or Q, I'm looking for zeros in both. That will make it false, and otherwise it's true. And now I can do P or Q or R. That means I'm going to look at these 2 columns, and when they have common zeros, then I get a 0, otherwise I get a 1. Okay, so let's see, that is going to happen here, right? That's a 0, but everywhere else at least there's a 1. Okay, so all 1. Okay, now we need not P, we need not Q, and not R. Okay, that's easy. 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. not P or not Q. Let's do that first. We have to do this whole thing, but we have to break it down. So not P, not Q. We're looking for zeros in these two guys, and that's happening in the two first rows. So a 0 here, a 0 here, but everything else is a 1. And now I have to I'm getting out a bit of space, so let me a little bit smaller here, not R, right? So now I'm looking at these two columns and looking for a common 0 that will give me 0, but otherwise I get 1s. So let's see, I get a 0 here, but everything else I think is a 1, right? Yep. Okay. And so what's now the actual thing, the whole thing? That's the end. Between the end, we have to take the conjunction, let's use the fancy word for it, of this and this. And this, in other words, we know this is going to be false when we have at least, no, it's going to be true if we have ones in everywhere. So do we have ones everywhere here and ones everywhere there? Yeah, there are several ones, right? Quite a lot actually. So we have it here, 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 here. It's just the two outer ones don't. Let me mark them if you, because I got a little bit lost, so probably you too. Yeah, these two ones. So, yep, okay. So now, is this satisfiable? Let's answer the question. Is this a satisfiable expression? Well, is there at least one 1 here? Well, there are a lot of 1s. Yes. So the answer is yes, it is satisfiable. And even more importantly, we can say in which cases it is satisfiable. And notice it's satisfiable in any case as long as not all of them are true or not all of them are false. Okay, this is something that you can figure out. There are, as applications of this satisfiability, it's a very important problem. And for instance, a Sudoku puzzle can be formulated as a satisfiability problem. So if you have a Sudoku, if you don't know what a Sudoku is, read in the, I'm not going to explain it, read the textbook, it explains it there, but you'll see it's a bunch of it's a long, very complicated propositional expression that the puzzle is solvable even only if you can satisfy that condition. But it involves so many variables that there's no way that you can make a truth table. So that's not the way to solve a Sudoku puzzle. Okay? And that's a bit the problem, is that, as I said, satisfiability, very often we have many different conditions that have to be met at the same time, right? And the question is, can we all meet them at the same time? And if there are 3, okay, we have 8 rows that we have to verify. If there's 4, 16, still possible. But think about searches in databases considering hundreds of thousands of variables. That's horrible, right? That's 2 to the 1,000. That is more than there are atoms in the universe. So it's never going to be possible to do this with truth tables. But that's an issue that we will discuss much later. I mean, not much later, but later in the course. Okay. So that's it for the logical equivalences, and I'm going to give you a lot of homeworks to do this, and then we can use this. This is important because we're going to again use this in the next section.